it turns out, realistically, in most systems, there's going to be some friction or some drag. For example, here, our pendulum has come to rest. Something stopped it. Something took its energy away. It no longer has the potential and kinetic energy that it had before. And in this case, it's primarily friction between the little string and the holder up here. So realistically, most systems will decay with time. So if we were to graph the motion, instead of being a nice perfect amplitude the whole time, the motion will die down and eventually stop. This equation our generic equation that we introduced assumes a constant amplitude the whole time. So it's assuming there's no friction and no drag in the system at all. So it assumes that there's nothing being lost. Realistically, there's always some sort of friction. There's always some sort of drag. So if you're not forcing it to keep oscillating, then the amplitude will die down with time. So your function ends up being a little bit different. It will still have a cosine term, but it also needs a term that describes the decay of the amplitude. Now, the way I've drawn it makes it look like it's decaying linearly. It's not really going to decay linearly. It's my problematic ability of drawing things. Generally, for example, with drag, if you had drag acting on your object, this decay would actually be exponential. So it would be more like that. So your function that describes the position of your object at any point in time, it's going to have an original amplitude. So capital A subscript of 0 is the original maximum value it reaches away from equilibrium. But then we need an exponential function. The exponential describes the decay of the amplitude. And then we need a cosine portion to describe the oscillation portion. So the function gets kind of big and ugly. This A naught times the exponential, that is the amplitude of your system as a function of time.
Is that omega prime?
Yes, I'll tell you what it is in just a second. It doesn't mean take the derivative of omega. It's only in calculus that you use the primes to represent derivatives. Don't do it in physics or engineering. So this front portion, the A naught e to the negative bt over 2m, that describes what's happening to the amplitude specifically. So that tells you how the amplitude is changing, the rate at which it's dying out. The cosine term is describing the oscillations. Omega prime with drag, your system actually oscillates at something other than the natural frequency. Okay? Drag affects the frequency it can oscillate at. So omega prime depends upon omega naught. We call these omega naught values, the natural frequencies. So omega prime depends on those, and I can't remember if it's a plus or minus sign, so let me look at it. Minus. So the rate it actually oscillates at is dependent on not only what it naturally would do, but also the drag. B is the drag coefficient. It has units of kilograms per second. So the drag coefficient is a measure of how big drag is. The bigger B is, the more significant the drag force is. The smaller B is, the less significant the drag force is. So omega naught is those natural frequencies. So if you have a mass spring system, it's the square root of K over M. If you have a simple pendulum, it's the square root of G over L.
So the amplitude is coefficient of friction, but
No, amplitude depends upon drag as well here. That's a B. So e to the negative bt over 2m.
so we look at drag, not the actual friction going on inside the cylinder.
Right. So here we're just looking at drag. So for example, let's say we have a mass oscillating on a spring again. The mass is 200 grams, the spring constant is 80 newtons per meter. But there's drag. So let's say there's a drag coefficient of 0.04 kilograms per second. It could be, yes. Yeah, drag, that's going to be more along the lines of maybe making our object oscillate in a vat of honey, sort of thing. So you could make it so drag is really significant. So a little different than the coefficient friction. So mass on a spring, the mass is 200 grams, the spring constant is 80 newtons per meter, the drag coefficient is 0.04 kilograms per second. I'd like to know how long will it take for the amplitude to decrease to half of its original value. So this amplitude's dying. At some point, we're going to have half of whatever the original amplitude was. I want to know what time that occurs at. Now, I know that the actual object isn't at that point. That doesn't matter. We just want to know where the amplitude would have that value. Okay? So we don't care about the equation as a whole. This equation as a whole tells us exactly where my object would be at any point in time. Our question is only asking us about what's happening to the amplitude. So all we need is the portion of this equation that describes the amplitude alone. Okay? So we want the value. This is the value that we want it to have. So A of t is 1/2 A naught. So that equals A naught e to the negative bt over 2m. Turns out the A naughts cancel, so it doesn't really matter what the amplitude was originally, because we just want half of whatever it was. So the original value cancels out. So we get 1/2 is equal to e to the negative bt over 2m. T's up in that power. How do we get the power out? Natural log of both sides. So natural log of 1/2. Natural log of the exponential function gives us the power. So T will be, I'm going to bring the 2m up, and the negative b over. So negative 2 mass, for our units to work out, B has units of kilograms per second. Our mass needs to be in kilograms as well for our units to work. So 0.2 kilograms, natural log of 1/2, all over 0.04 kilograms per second. The natural log of 1/2 is going to give us a negative value, which will cancel with this negative sign, so we won't get a negative answer overall. I don't know how to take the natural log on this guy. Has someone done this?
Yeah, 6.93.
Fabulous, thank you. And units, the kilograms cancel. The seconds come up to the top. So we get units of seconds for our time.